Okay, can you hear my see my screen now?
I can.
Okay, great. Okay, welcome to this webinar on time-variant behaviors of fault in magmatic systems and related hazard. And as Andy was mentioning earlier, this is sort of like a series of webinar that we are going to talk about. So basically today, what I'll do is to do a pretty good quick overview by myself, and there will be two short talks, one by John Gumberg from USGS on slow seep earthquakes, and another talk by Falk Amlon from University of Miami on volcano geodesy. Those talks are meant to not only just to show what are the recent, advanced and also future directions, but also hopefully give us some idea to open up for discussion later. And we hope to keep that, about 20 within 30 minutes or so, and then we have about the rest time will be open up for discussion. Like Andy was saying, that the best way, if you have any questions, would be writing those questions, with the text box and send it to me, and I will read it over out to the rest, and if I cannot address it, and somebody else can reply at the same time as well. Okay. So a little bit more again. I'll be brief here, just to tell you a little bit why we're here. So as you probably know, that this May there will be a workshop on future seismic and geodetic facility needed in geoscience. The workshop will be in Leesburg in Virginia, and because not everybody will get a chance to go to attend the workshop, it was been decided that there will be a series of webinars. So this is one of them. There are already 4. I mean, there are a total of 4. I think 2 already have happened. And this is the third one, and there's one more tomorrow on earth structure, biology, and geodynamics. So you can, for those ones that have happened, I think you can either view the agenda on the website, or the one that happened last Thursday, you can also watch the webinars online as well. And like Andy mentioned, this one will also be recorded, and unless anybody have any objections, it will be posted on the RS website later as well. Again, the goal of this webinar is generally to give you a chance to define sort of key scientific questions that are related to faulting process and magmatic systems, and also their associated hazard. And also perhaps think about what do we need to achieve this sort of goals or target. Identify potential facilities, both in terms of seismic, geodetic, magnetic, infrasound, and also others that are needed to address and also to make progress in those directions. And basically, what happens during the workshop, so that will be in the May, during the workshop, there will be 2 sessions associated with this topic, basically on faulting and magmatic systems. So those are the speakers that have already been identified. So during that time, they will give a much more, detailed talks on each of the topics, focused on earthquake process, magmatic process by Paul Segal, and also Richard Arlen was going to give a little bit talk about earthquake early warning. And finally, there will be a breakout session at the workshop in May, which talk about in the case of long-term observatory, short-term, and also what are the new type of observations, and how do we use seismic geodetic data to enhance the society use as well. So that's pretty much a quick introduction. And the final thing before I give the stage to the 2 speakers is to kind of remind you that there's also another, so beyond this webinar, there's another venue for you to provide your input, that is to submit white papers. And those white papers are pretty simple and straightforward. They generally have, at least the questions here. Those are the type of questions that we ask, while we provide those white papers, and they're due until 2 weeks from now. So in case you didn't have a chance to either speak or provide your comments, this will be another chance for you to do that as well. And I guess before I introduce the first short talk, and let me take a look and see if I can identify who has been here. As I see, so right now we have about total of about 38 people, and about 10 of them replied, and write their names and their affiliations and also what their primary interest. So in case you want to be identified here, this is the chance for you to write your names and also your affiliations and interests. I will read them very quickly, so hopefully it won't take too much of time. First is Bill Hubbard from University of Pittsburgh. Interest is geophysics and seismicity. There's a whole group of people from Pascal facility. Piena, Lowe, Justin Sweet, Ken Anderson. Bob Dietrich is IRA's president, interested in marine seismology. Lucy Fletch from Purdue University, one of the workshop organizers. Leo Bartlow from, I believe, UCSD, interested in subduction zone geodesy, sleep budget, and relationship between slow sleep and mega thrust event. Jessica Murray from USGS Menlo Park, interested in cross deformation from geodetic modeling and also use geodesy for real-time earthquake response. Anna Kenbert from Oregon State University, interested in MT and global electromagnetics. Yunli Fu from JPL, interested in slow sleep event and tremor. Bill Barhat from University of Iowa, interested in tectonic geodesy. Catherine Hodgkinson from UNAVCO, and Jane Somber from NASA Goddard. M. Meltzer from Lehigh University, interested in seismology. Bill Hammer, University of Nevada. Dongdong Yao from Georgia Tech seismology. And finally, Andy Barber from USGS Menlo Park, interested in string, pore pressure, fluid, and fault. I'm sure there are probably more people either will come later or I haven't identified your name, but those are the names that who have replied so far. So without further ado, I would like to introduce the first short talk by Dr. John Gumberg from USGS Seattle. So I'll give the stage to you, John, and you will speak, and just let me know when to flip the page. Thank you.
Okay, can everybody hear me?
I can.
Okay.
Yes.
Okay, next slide, please.
Sure.
So Zhigang asked me to kind of review where we came from, how we've got there, and then I'll give you a few ideas about what I think the future holds or ought to hold anyway. So I drew upon there are two grand challenge documents. One was written for seismology, and the other, and this should say geodesy, not geology. Sorry about that. And basically they covered a lot of the same topics and recommendations, and I think the recommendations could pretty much be summarized in these four things that we needed. So this was as of 2009. We needed to just make our monitoring better, denser, continuous, higher rate, etc. We needed more integration of not only seismology and geodesy, but probably also geology and other things. We needed to expand geographically and technically and develop capabilities to respond to earthquakes and other significant events that were learning opportunities. Both of these Grand Challenge documents outline a number of questions, many questions. I'm just going to illustrate that in a number of slides that we have made a lot of progress on answering a lot of these questions. I think the biggest lesson from all this progress has been the really important role of, and I won't say completely aseismic, but mostly aseismic slip, since there's really nothing is totally aseismic. But what we've learned, I think, and I've just listed the different types, is that there's most often the range of slip is, there's a seismic component and an aseismic component, and they go hand in hand most often. Sometimes one is measurable, but here's just a list of a number of papers and examples of where we need to observe both phenomena, or the range, the total range of slip phenomena. Next slide, please. So just a few examples with some of the questions. So in the blue box in the lower right corner is a question that was asked in both of the Grand Challenge documents. And one is, what's the relationship between slow slip phenomena and great earthquakes? We certainly, we don't have a lot of direct examples of that at the moment, although I show one, but we're learning about the connection between earthquakes and slow phenomena, and certainly there's it appears as this is an example for two slow slip events in New Zealand, that the earthquakes tend to occur geographically adjacent to where the slow slip is occurring. Next slide. Okay, and this one illustrates, I think this is a tremendous example of how we're beginning to learn what parts of the resolution is really giving us a view of the variability even on an individual fault. This is from Taiwan, and the GPS signals attributed to various portions of the fault after a magnitude 6.8 earthquake in Taiwan. And you can see that as you at various locations on the fault, the behavior is very different. And now we can actually see this and measure it and quantify it, and then try to understand what gives rise to it. Next slide. Another question was, how do faults recover? Again, as it listed in the examples here, and this is a figure from Tohoku, we see we can map now where the coseismic slip is and where the after slip is. And curiously, here it occurs in the same place, so the fault keeps slipping. So we can map now the recovery process, and if we continue over the long haul, see how it recovers to the next earthquake. So this is a tremendous progress and is really exciting. Next slide. With continuous monitoring, this is an example from Mexico of multiple large-scale slow slip events. And by viewing multiple examples, we can see how things change and how stable they are. So just again, an illustration of how we're beginning to be able to look at how things evolve with time. Next slide. Obviously, for forecasting purposes, we want to know if there's preparatory processes that we can observe, and this is probably familiar to most people, that Tohoku provides some really tantalizing suggestions that yes, there are measurable precursory phenomena, and that things are neither fast nor slow in the same place. So this is a map of the region surrounding the Tohoku rupture. The pink is the coseismic slip area. Prior to Tohoku, there was a 7.3 foreshock, followed by an after slip zone, and lots of foreshocks, or whether those are aftershocks of the 7.3 or foreshocks to the Tohoku rupture is semantics perhaps. But we can see in this same fault area we have aseismic slip or slow slip, fast slip that generates earthquakes, and that these seem to make sense in terms of a preparatory process for a magnitude 9 earthquake. So I think this is, again, a kind of a game changer, and it gives us motivation to keep working and monitoring and so on. Next slide. So just a couple of the practical applications of this progress. The next slide, please. The first, and this was highlighted in both grand challenges, is earthquake early warning. This is from a figure by Minson and others of an application of the high rate GPS data to early warning. She's developed an algorithm to map in real time effectively not only the magnitude, and that's where GPS is really critical for these really big earthquakes, but the fault geometry, and to know it within a matter of minutes, at least to first order what the magnitude is and the fault that's rupturing, which is important for damage assessments and tsunami warning and so on. Next slide. Another example where the two data, and this is where it's been emphasized to integrate, where both the high rate GPS and seismic data are used simultaneously. This is work of Gang and others, where if they have them co-located, you kind of get the full spectrum of the earthquake, from very fast and high frequency to very slow and low frequency. And this is being implemented also for early warning purposes, but also in a retrospective analyses as well. Next slide. So finally, just two of the frontiers. These are my own opinions. There are certainly lots more. Next slide. I think this is a sort of iconic figure now from originally from Ide and others, where we look at earthquake scaling in terms of moment versus duration. There are many other earthquake parameters that we can look at. How do they vary with one another? But one of the things that is noteworthy about this, and the lower half below about 100 seconds are seismic observations. Longer than about a day are geodetic observations. You can interpret these as you like, but there's a big gap in the middle where it's thus far been very difficult to make observations. And this is, I think, clearly, if we're going to make sense out of this over many orders of magnitudes, we need to fill in this gap. Next slide. In my opinion, the one way to do this, and this is a matter of looking at smaller events on longer time scales. The one type of instrumentation that holds that has that capability to really lower the threshold, the detection threshold, are strain meters. It's just what's being installed. Next slide. And to illustrate that we can see things that may be somewhat more difficult to see in seismic data, for example. This is a figure from some strain meters in Central California. The top are time series from the strain meters, and the lower figures are from seismometers. And what you'll see in the red, between the red arrows, are very long period seismic waves, which you can see in the strain meter data, but not the seismic data. These have periods of hundreds of seconds, That's encouraging that there is information that we could get at potentially that aren't accessible otherwise. Next slide. And finally, I think a big frontier for many applications is to start monitoring offshore. A lot of the really important processes and so on happen beneath the oceans. Again, the Tohoku earthquake really illustrated that in spades. This is a figure from Newman and others where they analyzed data from GPS measured offshore, and really is about the only way to really confirm what the slip is like near the trench, which is important certainly for understanding the tsunami potential. Next slide. And again, we need both seismic and geodetic and probably other types of observations from offshore. This is a recent paper using data from an offshore study off Vancouver Island. The figure on the right shows the hypocenters using only the OBS data, and then the pink lines show how those depths change when we view things, we integrate the onshore observations with the offshore. You can see that makes a huge difference in the ability to really resolve the depths of earthquakes, which is one of the principal ways we know where the plate interface is, etc. And next slide. With that, I'll stop.
All right, thank you, Jill. So I think we have another talk coming up, so this will be a good time for you to start thinking if you have any questions to John's presentation, or if you have any thoughts about, again, what are your, interesting scientific questions, and also what do we need to achieve those goals, and if you would post your questions, write it. And then I'll read it over to the rest after the second presentation. Just to let you know, I think we have two additional people showed up from New Mexico Tech. Ronnie Grapin, correct me if I spell it wrong. Ronnie Grapinstein from New Mexico Tech on active tectonics, and Radiant Avera from New Mexico Tech as well on geodynamic modeling. So I think I will pass the stage to the second speaker, Falk Amnon from University of Miami. Falk?
Okay, thank you very much, Jigang. Can everybody hear me?
I can.
You can, okay, so it seems to work. Okay, very good. Yeah. Thank you for giving me the opportunity to talk briefly about what I think the new facility can do for volcano geodesy. So, well, over the last 30 years, we essentially found out that almost all volcanoes deform to some extent between eruptions and during eruptions. So the big science question is, what does the detected deformation tell us about what is going to happen with the unrest, what are the hazards, whether the volcano is going to erupt. And so I'm going to talk about volcano geodesy, and of course seismology is very important. For example, seismology can tell us, tomography can tell us where is the magma and how much is eruptible, and seismology is important for the conduit processes and the monitoring. Okay. So this slide on the right shows a recent paper by Juliet Biggs, which essentially shows that all the volcanoes, the observations of volcanic deformation. Next slide, please. Okay, the challenge number one is to capture pre-eruptive edifice-wide deformation, so you can have deformation of the entire volcano, or you can have localized deformation. And there's a number of recent studies which showed that many eruptions were preceded by some precursory edifice-wide inflation. For example, Augustine volcano in Alaska, there was over a few months, there was not much, a few centimeters, but there was certainly some deformation detected, which is due to the rise of magma closer to the surface. And another example is Sinabung volcano in Sumatra. This volcano didn't do anything for a long time. InSAR data showed about 10 centimeters of uplift over a few years time period, and then this volcano was erupted indeed. So that volcano did what we want the volcano to do, to inflate first, and so we can say then something about that there's a possibility for an eruption. So the question, of course, is not always inflation leads to eruption. So in which cases does the inflation mean that the volcano is going to erupt? Next one, please. Okay, that was the edifice-wide deformation, and the other one is a summit deformation. For example, the eruption of Merapi in 2010, a very big one. It was preceded by a 1/10 of meter of summit deformation just in the days or hours prior to the eruption. And synthetic aperture radar, the backscatter images were very important to see that, and was also detected by EDM measurements. And so what probably is happening is you have a volcano in unrest, and then you move part of the summit away, and then you can get decompression of the magmatic system, and the magma can ascend as a result. So that's important to see it, and there's a recent study at Colima volcano by the group from Potsdam. They used a high-resolution satellite, TerraSAR-X, and they saw deformation up to 10 centimeter. Just so they had an image just acquired hours prior to a dome collapse, and this image showed that there was some precursory deformation. So apparently, so it looks like there's some geophysical precursor which can be detected prior to dome collapses, which are of course very dangerous because of the pyroclastic flows. Next one, please. Okay, so I think what we can do, or what is an opportunity, there's these spiders. There's one developed by the USGS, which has seismograph and also a GPS. In a case of unrest, you can easily deploy that with a helicopter on a volcano. Well, for the USGS one, you need a helicopter, but now we have drones. You could put these kind of instruments on drones in the case of an unrest, and the Earthquake Research Institute in Tokyo, they have an unmanned helicopter for these kind of things. And I think that is something what a facility could do, to have these instruments ready, or that is something what we should be doing in the future when there is some unrest, to really get some good scientific data, taking advantage of this scientific opportunity of volcanic unrest. In particular, useful will be to get, for example, GPS data right from the summit to get the high resolution, and when there's an earthquake somewhere nearby, then okay, we can better understand earthquake-volcano interaction. Next one. Next one, please. And the other opportunities are global volcano observations using InSAR. So we are fortunate now. We just got a new European satellite, the Sentinel-1A, last year. It's globally observing, and we will have an opportunity to detect ground deformation at volcanoes which are not monitored otherwise. And so the plan should be to use the globally observing volcano SARs for background observations, and then when we see something, then we can use high-resolution sensors to look for summit deformation, or to monitor summit deformation, and maybe deploy in situ measurements or these spider-type instruments on volcanoes which are showing some unrest. And a particular opportunity is the new SAR mission from NASA and ISRO called NISAR. The launch is in 2020, so finally we're getting a USR mission, and maybe around, so that's going to provide excellent imagery, and around that mission maybe we can develop some kind of program for global volcano monitoring. And there's a number of other, actually lots of SAR missions with restricted data access, including ALOS-2, RADARSAT-2, Cosmos Skymet, TerraSAR-X, and Argentine mission SAOCOM, which soon will go online. And a facility can help to make those data available. We don't need necessarily help from the facility for NISAR and Sentinel-1, that is done by the space agencies, but for SAR data from space agencies, which or from satellite missions, which have a different purpose, we need a facility to make those data available for the scientific community. Next one, please. Okay, and just to highlight the recent white paper, community science position paper, which was actually released Saturday, I believe, from the European Science Foundation and the group on Earth observations. They looked at the extreme geohazards, and one of the main findings was that actually what poses the greatest threat to society are the large volcanic eruptions. For example, if you get a repeat of a Tambora-sized eruption, which was 200 years ago, there was this year without summer, that's going to have some bad consequences. And one recommendation was to develop a global volcano monitoring system to mitigate possible problems on food security and transportation. And maybe that is something what can be written in this proposals, especially given NSF's new focus on risk and resilience. Next one. Okay, so to summarize the facility needs, I think it would be nice to have something what helps with the scientific response in volcanic unrest. It should supplement VOVODAT. VOVODAT has data products. Increasing number of agencies, for example, in the Philippines and Indonesia, they are taking part to some extent in VOVODAT, but the raw data are not available. So that's what the facility could do. And then it would be nice if the facility has some kind of global aspect. I think in the past with UNAFCO or IRIS, I know less, but it was always seen as very much American. So many people didn't really, or in some countries, they don't want to have too much to do with the Americans. So if you could give it somehow an international component, for example, the ICE people have been very successful, or the international drilling program. I don't know how to do it, but it would be really nice if it had that, and would make it much easier to work in places like Indonesia, for example. And okay, it would be nice if there's some sort of coordination of international volcano unrest response, and I don't really know who would do that if it is not done by the next facility. And then there's a number of needs for SAR satellite. I don't want to go into details, but as I said, the basic thing is that many space agencies, they have other purposes, and the data are not. They would like to They would like that the data are used also for volcano studies, but they don't really have the possibility to make those data available, and there the new facility can play an important role as it does at the moment. Thank you very much. That's all.
All right. Thank you, Fob. So I think now we have about a little bit more than 20 minutes. This will be a good chance to talk a little bit about what you have any questions about the presentation we have today, or just generally what do you think are, again, primarily interesting questions that's going to happen in the next I would say 5 to 10 years perhaps, and also what specifically is needed. Again, we don't have to talk let's say too details about specifically instrumentations, but talk maybe focus more about like what type of data is needed. For example, what are potential spatial and temporal resolution, what are the accuracy, etc. I think I have one question from Leo Bartlow, and she was mainly addressing one of the important scientific goal was to basically characterizing our uncertainty, especially in sleep budget and locking models, for informing hazard forecast. Andy, is there a way you can unmute her and see if she would like to?
Sure. I'd be happy to. Let me go scroll down the list. I'll find your name, Noel. And if you're all right, I'm going to open up your mic now. So you should be live.
Can you hear me?
We can.
Okay, great.
Yes.
Hi. This is Noelle, and I just have been thinking a lot about slip budgets and especially locking models and how they're used for hazard forecasting, and how a lot of times locking models don't have well characterized uncertainties, and of course they're very uncertain offshore usually. So the obvious data that we need, of course, is offshore data, but usually the errors on offshore data are quite large. So I think we just need, as a community, to do a better job of exploring the range of models that could possibly fit the data, and figuring out what kind of uncertainties we have, and they should probably be spatially variable.
All right, thank you, Leo. Just to follow up on this, I guess you mentioned that we obviously we need more data, but the issue is offshore data is normally noisy. Do you have any suggestion or any general kind of comments about how to improve that aspect?
That's actually something I'm hoping to work on this year, because the offshore pressure data from New Zealand is supposed to come back in a few months, and I'm hoping to develop some techniques to better characterize that. And I also know that here at Scripps there's a new offshore pressure instruments being developed that solve one of the main problems with offshore pressure sensors is that they have a large amount of drift. It's usually in the order of centimeters per year, which is obviously a problem if you're trying to do a locking inversion. So here at Scripps, I know there are new instruments being developed that solve that drift problem. The issue is that they're currently very expensive.
All right.
So,
okay. Thank you. So we have another, I guess, question that comments from Jean Sauber, and she wrote basically that non-wave gravity changes from grace have been measured and can be integrated and modeled with other observations. Again, would you like to elaborate a bit more on that? Maybe again, I can see if Andy can open up mic. If not, I can. Andy, can you open up mic for Jen Sauber to see if she would like to speak a little more?
Oh, yes, I did. Sorry, I was muted when I said that.
Okay, sorry. Okay.
Yeah. So I don't know, Jean, if your mic is.
I keep losing the sound, so I didn't even know you opened it up until I saw the green.
Yeah. So you are live. We can hear you.
My mic is on. Do you hear me?
Yes. Sounds like she can't hear us though.
Okay.
But I didn't hear the question because for 1 minute I had no sound.
Okay, so maybe Zhigan, do you want to ask that question again?
I can now.
Okay, I was asking.
So I just wanted to encourage people.
Go ahead.
Go ahead,
Sorry,
Jean.
no sound.
Okay, maybe Jean.
I did not hear your question.
Okay, maybe we should.
I don't know what question I'm answering.
Okay, never mind. Okay, so you basically wrote like a question or comments about non-wave length gravity change from grace have been measured and can be integrated and modeled with other observation. I was asking whether you would like to elaborate more about whether this is the question or comments. But I guess there seems to be some connection problems with the voice. I also noticed, I think Louisiana also wrote that looks at in the second talk, the voice is coming intermittently. Hopefully right now the voice is not the issue anymore. I also heard some break in between. So I would say, are there any other questions or comments from the audience? So, because the way it's set up, I think right now the best way, if you have any, again, general questions or comments, would be to write them in the the question box and send it to us, and we will read it out. And if you like to talk, and you can let Andy know, and we will unmute you, even though sometimes this may or may not work properly. So one of the things, I guess, to keep things going, I have a few more slides which kind of act as a sort of way to show what I think are, or what are my questions that I consider to be interesting and important, and also what I could sort of my wish list. I'm just using that as a kind of like a time holder, and in case any of you have any other comments, questions, again, I would encourage to do it right now. We have about 15 minutes, and of course, if you prefer, we also have this white paper I mentioned at the beginning that you can go ahead and post your your thought and ideas about how and where the community should go next in terms of developing interesting directions, and also what are the needs we need to address. What I'm showing here, I guess, on the map is basically showing you the Earthscope station status as if basically right now. As you can see, basically, the US array, and also both the flexible and also the transport array has pretty much finished up deploying in the lower 48 US and is marching towards Alaska right now. Those data has been used by many of us to basically address what is the interesting need, not only to study the structures, but also study interesting phenomena associated with earthquakes and volcanoes. I do have a question pop up right now by Fiona Miller. The question is for John. The question is, could quiet broadband seismic stations see some of the string meter signal? So this question for John.
Oh, possibly. Yeah, I think there's probably improvements that could be made to the broadband systems, particularly again as you go to lower frequencies. But I'm probably not the one to comment on those. I suspect that some of the noise and so on comes from electronics and how they're constructed and so on. So I guess the bottom line is I don't really know how far they can be pushed. Maybe Andy Barber could comment on that. He's looked at the noise. It's really a matter of the noise characteristics, I think. Maybe Andrew Barber could comment if he's on.
Let's see. She's on, and I guess could Andy unmute her?
So Andrew has responded in a couple of comments about that in the question box.
Okay, I can read on those. I think Andy says, I would say that the best bet is with STS1, and perhaps STS2 is perhaps not. So I guess some of the instruments might be, but my understanding is that there are many of this. Some of the STS1 has been upgraded to STS2. So I guess the answer would be some of them can, but not all of them. But that probably still will not completely solve that gap, which is between a few hundred seconds up to perhaps a day or so. And Andy also wrote that it also does most certainly depend on the noise level as well. So, if you're on the quiet side, perhaps, but if you're on the noisy side, maybe not. Okay. So any other questions or comments? If not, then I have just a few slides again. Like I said, I will just keep going unless somebody else have questions or comments pop up. So this is sort of, I consider it to be my wish list. Again, like I said, my one of the quick things summarized from let's say what happens in the past 10 years, at least in the field of seismology, is that basically major breakthroughs in the past decades mostly came from analyzing unwanted signal. In some cases, what we call as noise. This including let's say deep tectonic tremor, and also to use ambient noise as a way to do seismic tomography. And finally, also sometimes it also including what we call as unexpected source. For example, when we put the US array, nobody expected that we're going to record a lot of the so-called injection-induced earthquake in central and eastern US. And turns out that the US array, and also of course other stations are providing much more information about how those occur, and this is sort of like a relatively new phenomenon. We still don't know much about it, how those events occur, and also how does this compare with, regular earthquake in those regions, which normally we don't have a lot of events. So that's, so I think, we would encourage all of you to think about, perhaps while, we were thinking about what are the next big things, might happen in our field, whether we may have any sort of target or signals that may have already been recorded, but nobody have actually analyzed or studied before. And this would actually hopefully open up some new directions as well. So, again, the way how I see it, in this side, mostly speaking in terms of seismology, is what I consider the future of seismology is it's like, the motto of Olympics, like faster and higher and stronger. I have 4 of them. The wish list I would like to see is basically first denser. There has been some recent new development in terms of using seismic node for very ultra high dense deployment. For again high resolution imaging of subsurface structures, in particular focusing around active fault, and whether we can achieve, let's say, on the scale of I would say maybe meters to tens of meters if we have enough dense instrumentation. The second is basically go deeper. That is, as you know, in order to better characterize what's going on at depths, especially near the source region, we need to have stations that are placed at very close to the source as possible to remove potential past and also side effects. So deep borehole recording, which has been done before, as part of the SafeOut effort, and also in many other regions around the world, they have established, many fault zone observatories. Those are, things we can think about. And finally, faster ways to not only transfer data but also compute and disseminate information for early warning purposes, and also wider in terms of spatial coverage, especially offshore. I think that's something which was mentioned before as well. We have a few questions. I will also read them off to you. One question is by Bill Barnhart, and he wrote that another thing to consider is by the so-called SAGE or GAGE facility is moving towards more complete integration of geodetic and seismologic data, particularly where similar sampling rate available. This could simply mean finding ways to make high-rate GPS series available in seed format with appropriate and community-guided metadata and processing, etc. this is he also wrote this is already done with stream meter data, and it might make sense to bring GPS as well. I think this is the excellent point that if we want to think about what's going to happen in the future, is that many of the recent new discoveries made is by a combination of seismic and geodetic study. So if we can find an easy way to make the data available and also easily used by other communities. So not only, let's say, seismology use geodetic data and perhaps vice versa, how would geodesists use seismic data? So that would actually hopefully bring down the barrier and perhaps open up for more interesting new discoveries. As far as I know, I think there are some very limited GPS, high-rate GPS data, I think, associated with, let's say, 2002 Denali earthquake, magnitude 7.9 earthquake. And I think that those data are available at IRIS website, but there hasn't been a lot added recently. So that's something perhaps we can think about how we can merge those two data sets, perhaps with even one data center that can serve both communities. Those are something we can think about. If anybody have any, response to that, what I just described, you can type in as well. Another comment by Luciana Astis from UCSD is that it looks like this is a response of the previous question about whether we can use broadband sensors to observe a very long period signals. Her response is that there are new broadband instruments that have no noise floor, like nanometrics tritium 240, which has a broader response than the early model of 120s and also STS2, and which have their for those which have their response flat only to 120 seconds instead of 240 seconds. So those nanometric tritium seem to have a broader response in a longer period. In addition, she wrote that the STS1 sensors had flat response to 300 seconds. The problem that Joan was addressing between 100 seconds to 1 day, which is about, of course, 86,400 seconds, is a tricky problem, as there's environmental noise and tidal modes that affect or but recorded by seismometers that may be larger than some signals. So the tidal modes will also affect stream meters, so there may be a problem. There may not be a problem. So I guess she wrote that good installation procedures go a long way to insulate seismometers from temperature and atmosphere pressure daily fluctuation. So I think there seems to be a challenge for us to think, to consider is whether we can use those ultra broadband sensor to observe signal between hundreds to a day or so. And one more comment, I guess, is the response from Bill Barnhart is he wrote that related to the question of sharing the the GPS data with seismologists. He wrote that this is already done with the stream meter data, and it might make sense to bring GPS in as well. Yeah, I think this is an excellent point, and hopefully this could be maybe something to think about, for folks that are going to the workshop in May. Now, I think we have about 2 minutes left. Now, I would like to ask one last chance. Does anybody else has any questions, comments? If not, I would say that we can begin to close the workshop. So I want to, before we close, I would like to thank our two speakers, John Gumberg and Folk Emlon, for volunteering to give their talk. I would like to also thank Margaret Bocher. I forgot to introduce her. She is the scribe of this webinar, and both of us will write up from your input here and present it at the workshop in May. And finally, like Andy was saying, that basically this webinar will be is recorded and will be posted on the website, unless anybody have any objections. And if not, I think I'll pass the stage back to Andy. And thank you all for attending the webinar.
All right, thanks everyone, and just a reminder that we have one more webinar scheduled at 3 p.m. tomorrow, and that is Maureen Long from Yale talking about Earth structure, rheology, and dynamics. So if you're not registered for that already and you're interested, please do, and hopefully we'll see you there. So thanks, Shigong, and the other presenters, and we'll see you back here tomorrow. Bye-bye.